content of clover and grass in the sward using a consumer camera and Mortensen. Right now I'm working as a research assistant at the University of Aarhus, and this work has been performed at the University of Aarhus as part of my So a small outline of my presentation. First I'll tell you about the motivation behind this work. Then I'll briefly talk about the test bed and how we acquired the data. I'll of course show you the methodology and then present the results. And finally a small conclusion on how we can improve this in the future. So the motivation behind this is that, well, clover and grass is sown in Denmark at least as a catch crop and also used as a feed crop for dairy cows. However, we know the mixture that we sow, but we don't really know how much of this comes out of the soil again, so to speak. So it's unknown what the distribution in the field is. So when we harvest it and use it as feed for the cattle, we don't know what the distribution between the clover and the grass is, and it has a huge impact on their milk yield and their intake. And also when used as a catch crop, the amount of clover in this the field determines how much nitrogen we can sort of extract from the soil. The current methods to sort of determine the distribution is destructive analysis, where you cut a subsample of the field, and then you take to your laboratory and you sort of divide the species you want to know about, and then do a dry matter analysis. It's very cumbersome and takes a lot of time, and it's not ideal if you want to do it on a whole field, but it's alright for small plot experiments. So we did a plot experiment in 2013 here at Research Center Forum in Denmark. We used two different seed mixtures, called mixture 35 and mixture 45, with whitegrass and white clover, and whitegrass and fescue and red clover and white clover. For the further work on this, we just regarded red and white clover as the same species. So we just looked at grass and clover. The plots were photographed and on 4 different occasions, and 3 days, or 3 days after the photos were taken, the plot was cut and was analyzed in the lab. We gathered a total of 45 images, and the dry matter varied from around 200 kilograms per hectare to 6,000. And the clover in the analysis will range from 10 to 72% of the dry matter, and the grass from 26 to 90, and we had a little bit of wheat as well. Just to illustrate how we gathered the images, we have our technician David here, and we have a long microphone boom with a camera, consumer camera, mounted at the end, facing down, and then using the remote, captured the images, which look somewhat like this. And it's in this sort of mixture that we want to detect the areas with clover and the areas with grass and distinguish these. From these 45 images, because we want to determine the coverage first, we sort of extracted 28 small patches like this one, where we manually annotated the clover and grass content, as you see over here. So the yellow areas is clover, and the light blue is grass, and the dark blue is sort of background, and the orange is the clover flowers. Our method is seen here, the overview. So the first thing we do is that we classify the illumination. And based on that, we select the parameters that we use for estimating the coverage, and finally the parameters we use for transforming the coverage to dry matter distribution. The reason we classify the illumination is that we have two very distinguished illumination cases. We have one in indirect light. We hardly have any shadows here. It's whereas in the direct sunlight we have a lot of shadows on the clover, which causes some problems or can cause problems. So the way we distinguish between these two is that we make a histogram of the image, as you see down here. We have the two different cases, the red and the blue, and based on our training case, we have this mean histogram, and then we use a cross correlation to sort of see which histogram does our test image match of the two mean histograms. It works fairly well. There are better ways of comparing histograms, but this works fine. So the overall method we do for estimating the coverage, as seen here, is based on a method from a guy called Bonesmo and some other ones, but there are some differences. We start with our input image up here, and then we start by removing the background, which we regard as soil, the plant material, and deep shadows. So we remove the soil and dead plant materials, as Morten talked about, by using excess green, and then remove the shadows, as you see up here, by a simple threshold in the green image, or excess green image. And the reason we remove these deep shadows is because although it's plant material, we can't distinguish the grass or the clover anymore. Next, we try to extract the clover leaves by creating an inverted edge image. And the idea is that the clover will have large patches, whereas the grass will be small patches, and then we erode this image several times. And the idea is then that the grass will vanish from this mask. Then we take sort of the center of mass of each of these blobs and find the corresponding blob in this original inverted edge image to get the correct circumference of the shape of the clovers. Then we grow it a little bit again to sort of the edges to circles or getting back. And then anything that we don't regard as clover in the green image we regard as grass. So the final result you can see here, where the blue areas are the clover and the green are the grass and the red is the background. And as you can see, there are some wrong classifications, as this grass straw is regarded as clover. And we did the training on the small patches, I'll show you. When we have the coverage, we want to transform it into the dry matter distribution. We tried just a simple linear transformation, and it worked quite well. We have 4 different cases because we have the different light conditions, and then we have clover and grass, and we make a transformation for each case. And it seems to work quite well. The only downside to this is that due to the transformation, one of the points in our test set fell outside of the valid range. So we should probably use something like log transformation instead, and then a linear transformation on that one to avoid that. From the coverage estimation, we present our results in a confusion matrix, which should be read as this is how we have labeled our data. So, for instance, and this is how we have detected it in the direct sunlight case. So, for instance, we have shallow soil, grass, clover, clover flowers, and wheat. So, out of all the clover pixels, 30% of those classifies as shadows, and 0% of those as soil, but 39% as grass, which is not too good, and only about half of them we actually classify as clover. In the indirect case, it's a little bit better. We have around 65 68% of the grass and clover which are classified correctly, and only about 20 to 30% which is falsely classified between those two classes. If we look at the overall results of the dry matter distribution, on our training set you get mean absolute error of about 8.6 and 9.2 percent points. So if we, for instance, estimate a value, then it's within, on average, 8.6 or 9.2 percent points. On our test set we get a little smaller error, which is a good thing. And we tried to test to see if there were any correlation between the two mixtures and the error and the dry matter, or the true clover dry matter and the true total dry matter, but we didn't see any apparent correlation between those. Yeah, so to make a small conclusion, it's definitely possible within a reasonable accuracy to estimate the distribution. Some of the agronomic people I've talked to, they said, well, they would really prefer if we could go down to 5% because then they can really use it. 8-9% is still a little bit too much. Our greatest error source is this cover estimation, as we saw especially in the direct sunlight case because of the shadows. So a good place to sort of see for improvement would be on that. And I think that texture analysis would perhaps help a little bit there. I think we've gone as far as we can with this I can't remember much. Sorry about that. Also, the illumination model right now is sort of binary, either it's sunlight or not sunlight, and that's not how it works in real life. It's more, should be more continuous. And also, we've used just a linear transformation, perhaps to produce a more natural model for it, including something like the time since last harvest, or the temperature, sun, or available water, or the expected yield. That's all for me. Thank you for listening.
Thank you very much.